Concrete is often dismissed as a simple, static building block. But to a civil engineer, it is a dynamic, living material. It is the only structural element we manufacture on-site, which means the chemistry is in our hands. If you understand concrete, you understand the backbone of modern infrastructure. Today, we aren't just looking at a recipe. We are exploring the molecular bond of hydration, the physics of composite materials, and the engineering decisions that determine whether a structure lasts 50 years or 500. The most common misconception is that concrete dries. In reality, it hydrates. When Portland cement hits water, it triggers a series of exothermic chemical reactions. The most important byproduct of this reaction is calcium silicate hydrate. This gel grows like microscopic needles, interlocking with one another and gluing the aggregates together. This process isn't instant. While concrete achieves its nominal strength at 28 days, hydration can actually continue for years, as long as moisture and unreacted cement are present. To teach this as a proper class, we must look at concrete as a two-phase composite. 1. The discontinuous phase, aggregates. These make up 60% to 75% of the volume. We use a well-graded mix, meaning we have a specific ratio of large stones down to fine sand. The goal? To minimize the space between them. 2. The continuous phase, cement paste. This fills the gaps. If your aggregates aren't well graded, you need more paste, which makes the concrete more expensive and prone to shrinkage cracks. In 1918, Duff Abrams discovered the most important law in concrete technology. The strength of concrete is inversely proportional to the water-cement ratio. Think of it this way. Water has two jobs. One is chemical, hydration, and the other is physical, workability. If you add water for workability that isn't needed for hydration, that water eventually evaporates. This leaves behind capillary pores. These pores are the enemy. They reduce compressive strength and provide a highway for salt and chlorides to reach your steel reinforcement, leading to concrete cancer or spalling. Why do we put steel in concrete? Because concrete is brittle. It's like a digestive biscuit, strong if you squeeze it, but it snaps the moment you bend it. When a beam deflects, the top fibers are in compression and the bottom fibers are in tension. We place steel rebar in that bottom, tension zone. Because steel and concrete have almost identical coefficients of thermal expansion, they expand and contract together, ensuring the bond never breaks under temperature swings. If this lecture helped you, please hit the like button and subscribe to my channel.